Okay, so we continue this section of this course devoted to the open quantum systems and dynamics of open quantum systems. Our example, and the only example that I want to talk about here, is so-called the leaky cavity. So, just as last week, we imagined a cavity and one particular mode with a frequency capital omega, which is coupled to C of other modes, also considered to be harmonic oscillators. Creation and annihilation operators for these other modes will be denoted by B, and little omega j will be the relevant frequency of a given mode. Important simplification is due to the fact that we will assume something which is almost identical to the rotating wave approximation. So our Hamiltonian, again, like last week, will be of the following form. Yes, and the interaction, also let's pull out the H bar, and the interaction is the sum over J with some couplings Gj. Couplings could be complex, but I assume they are real. That is of no relevance. It's not any particular simplification. And what you see here is that, of course, it's a Hermitian operator, but it concerns the number of quanta, so to say. Yes? If something outside of this cavity in the bath or reservoir is destroyed, then simultaneously photon appears inside, and similarly here, if photon disappears from the cavity, then it does appear in some form. Something like semi-phenomenologically, we've discussed this open dynamics or dynamics of the subsystem, talking to these bath oscillators, last week, using description in the Heisenberg picture. So our operators were changing in time, and we said that we noticed that one can describe the dynamics of the creation of the annihilation operator inside with some kind of a damped factor. So say, in Heisenberg picture, we could write minus kappa times A plus this famous Langevin term, and given proper commutator of the Langevin operator, 2 kappa delta of t minus t prime, given this, we could check that this is indeed a unitary evolution for A, just because if we solve this, assume this, then the commutator of A with A dagger, even though itself this fellow is damped, nevertheless retains value of 1. I also briefly sketched, so to say, the elevation of this equation, this Heisenberg equation, starting from this Hamiltonian, and as you remember, I again invoked the string with a Laplace domain and the single pole approximation, and in this approximation, the equation takes up this form, but it's not completely trivial to cheat the audience to the point of deriving through delta. There is some kind of a smearing that pops up. But such a term is, of course, present, and this term is a combination of all these B operators. That's it. Now, today, we jump to the Schrödinger picture. In other words, we want to describe now the behavior of a system system itself, not of its operators, but behavior of the system itself. So our starting point is what some people call von Neumann equation, some other people call, how other people call it, I don't remember now, but I will call it von Neumann equation for the density matrix of the total system. Means field inside plus a buff. And of course, this is minus I over H commutator of total Hamiltonian with rho total. Now, this is of course equation which is not trivial to solve. One can do a lot with this particular Hamiltonian exactly, but this is not our aim. Our aim is to derive the reduced equation, an equation for the density matrix of our subsystem, which by definition is the same as the trace of a total law with respect to the buff, with respect to the variables of the reservoir. We don't want to think of behavior of all degrees of freedom. We are interested in the behavior of what is inside. And the buff, we think, is huge, has infinitely many modes, consists of the rest of the universe. So it makes sense to assume that this subsystem, which is a reservoir, all this rest, so to say, has evolution, has no evolution, has evolution which does not fear this little photon or two that could emerge from the cavity. So, for the buff rho, we will assume something which is almost obvious, namely that this is canonical distribution of the thermal state. It need not be so. What I'm writing now is limiting our attention to some special situations, rather common, right? Usually outside there is a well-known, well-defined, not well-known, but well-defined temperature. It could be the residual light field from the Big Bang or whatever, yes, but really something of a well-defined temperature. So which would be E to minus Hamiltonian of this buff divided by the Boltzmann factor, Boltzmann constant times temperature divided by Z. And of course, this, what I call HB, is H bar sum over omega J, Bj J, which means that since this is a sum, that in each mode there is a thermal equilibrium, so thermodynamics of a single oscillator is really called for, right? So for the one given mode, rho J, I can immediately write this in the form H bar omega divided by kBt sum over n, for instance, n projection on n, still divided by z. We were playing such games. Z is of course a trace of this exponent thing. Now this trace is of course a summation of a geometric series. This is something that we have already seen. This is 1 divided 1 minus psi, where psi is my favorite abbreviation for H bar omega divided by kBt. Yes? And also state of temperature capital T. And then one can reverse expressing this by psi, and this probably you also remember it is the same as psi d by d psi of log z, right?
If there is G index in this law.
Oh, well, I dropped it, of course there should be, yes.
Oh,
Yeah, for everyone I do the same, yeah. That's a typical one.
Yeah.
That's good. Yeah. So, of course one can compute it, then reverse it, and then one finds, I do it very quickly just because I'm repeating what I've been telling you already, that the probability of finding exactly n photons in a temperature n is the mean value, let me call it k photons, it's a mean value n to power k divided by n plus 1 to power k plus 1. This 1 over n plus 1 comes from z, the rest is just showing that it's a geometric series. Okay, so that much we know and we care about our path. Once again, it's an assumption of great interest. I would say recently, by recently I mean over the last, say, 20 or 30 years, is also studied different paths, also huge, and also not subject to a particular influence of the small cavity which is leaking some photons. But, for instance, using language of modern quantum optics in states which are squeezed, for instance, then the behavior of the system is different than with the thermal state. But we are not here at the lecture on quantum optics, we are here at the lecture on applications of quantum mechanics. So it will be enough if we understand how the thermal equilibrium path acts on the cavity. Okay. So what's next? We can write the whole Hamiltonian in the form of H0, which is non-interacting part, plus interacting part, of course. And then, these are all these oscillators. The big oscillator with A Tucker plus sum of all the B oscillators. And this is the interacting part, the last step. Then, in our equation for the total row, we can go to what is called interaction picture. So we can define a row interaction picture total as, now I could figure out, but I better check to have signs in the right places. Which is e to I h0 t divided by h bar, this old regular row total, e to minus I h0 t divided by h.
So it's interaction.
This is called interaction picture. Interaction picture. It is something in the middle between Schrödinger picture and the Heisenberg picture. You remember, Schrödinger picture states evolve. Heisenberg picture states do not evolve, operators evolve. Interaction picture is halfway. Both states evolve and operators evolve. But what is taken already into account is the free evolution without the interaction. That's why it is called interaction picture. So now, defining this, I can derive equation satisfied by this fellow. I have to differentiate everywhere, yes, over t. So when I differentiate here and here, I pull out I over h bar times h0 either on this side or on this side with minus sign. So in other words, I get I over h bar times commutator of H0 with rho tilde total. Right? So this is first term, but the second term is, of course, I have to differentiate also this fellow and use the other equation. Yeah? So the first, in this remaining equation which I have here, I could have written, don't have my sponge. It's always hiding somewhere.
Oh, there's a...
Yeah. So I could write, of course, this as minus I over H bar, H naught, rho total, minus I over H bar, Hi, rho total, yes? What I want to say is that when doing so, out of this first term, I will get exactly the same thing as I have here, and that will cancel. So this will cancel against this. And what remains will be minus I over H bar. And here, I have all these two exponents outside. I have to put Hamiltonian of interaction with rho total. Then, of course, I have to, again, replace this rho total by the one with a tilde. And that combined is e to I H0t divided by H bar H interaction times e to minus I H0t with rho total in the interaction picture. So, as I promised, in the interaction picture, both state evolves, but also operators evolve. So I have to evaluate this fellow. Fortunately, this is very easy. So my Hamiltonian in the interaction picture is just the standard free evolution of creation annihilation operators which are there, yes? So it is simply H bar sum over G, say J. First term I wanted A times beta get, and then the A oscillates with minus I omega t, and B, J, oscillates with plus I omega j t, plus of course Hermitian conjugate, so plus A dagger Ej e to I omega t minus I omega j t. Okay, so this fellow must be substituted here. Right? Okay. So what next? Well, next, and that is typical, usually one is deriving the Schrödinger equation, for instance, in the interaction picture, to facilitate development of the perturbation theory. Why? Well, because in this interaction picture, our equation for this total of t only has interaction, yes? So it's minus I H bar hi of t rho total of t. So, as I say, it is calling for the use of the interaction feature, of the perturbation theory, just because we imagine that our cavity is pretty good. It oscillates like crazy, and once in a while, maybe once every million oscillations, a photon pops up, which means that indeed this is a weak interaction. Now, how to work out this thing? Formal, so to say, solution in quotation marks of this equation is, of course, it's not a solution, it's really transformation of this equation into integral form, is the initial value. At initial value, I do not need to wiggle because, of course, at t equals 0, these things coincide. Plus, well, minus in this case, minus I over h bar times integral from 0 to t of this business. It's not really a solution, it's a conversion of differential equation into integral equation, yes. Good. Plus, of course, higher order term. I'm sorry. This is exact. But now when I plug in here something trivial like the initial value or something, then I will have my solution in the first order. And so on and so on and so on. So one nice way of transforming this into something clever is to plug in this first order expansion here. By doing so, what we will achieve? Well, we will achieve expansion at the level of this equation to the second order in the interaction Hamiltonian. Yes? If we plug in here zeroth order term plus first order term and there's another interaction Hamiltonian here, then we will get expansion to the second order. So we will do it, but almost immediately, let's notice that we can simplify our life a little bit by completely dismissing the first order term. Why is it so? Well, it's very simple. Our aim, as I mentioned already several times, is to derive reduced equation for the reduced density matrix. So we are, very soon we will be taking a trace of both sides of our differential equation with respect to the path value. Now, if I take the first order term, namely, if I imagine substituting the constant to my equation, then what will happen? What will happen is that I will be taking average of B or B dagger in the first power with our density matrix of the path. I think all of you see that this is 0. Do you see it? Do you see it? Yes? Not sure. Let's do it. For one given mode, yes? If I have this fellow, this is nothing but a trace, I repeat, of B rho B. And this is the same as 1 over Z, sum over K, and then this e to minus h bar omega divided by K B T times K. And here I'm getting K operators, yes, and then one annihilation, which makes K minus 1 times K. In other words, and the trace, yes. In other words, what I'm getting a sum of operators which do not have diagonal elements, yes. So when I sum, when I take a trace, in other words, sum over n and this whole fellow n, then all the terms are 0. Yes? Everyone see it now? Here. Huh? Sure, of this given mode. And since this fellow, as I say, this fellow makes it curious, make it case on left and on the right are different, then the sum of diagonal elements must be 0 because all the elements are 0. Of course, the same will be dagger, yeah? So, in other words, we can do away with the first order term. Some achievement or some simplification, yes. So now, let me write more or less explicitly the second order term, or what we get to a second order. So I have to take my equation and plug in the first correction from this fellow, yes? So I have minus I over h bar squared first. So this is minus 1 over h bar squared. So this is minus 1 over h bar squared. I have integration with respect to tau from 0 to t. And now I have an awful thing. I have my interaction Hamiltonian in the interaction picture evaluated at time t. I commuted with this correction, which is another hi of tau with rho total of tau d tau. So that's my second order correction to the equation, and I have to still work hard to evaluate it further. First of all, we see that if I would work out this double commutator, then I would have terms of three different types. Either two Hamiltonians will be on the left of rho, or two Hamiltonians will be on the right of rho, or rho will be sandwiched between two Hamiltonians. Yes. So there are there are three types of terms. Now, each of these Hamiltonians, guys, is the sum of two terms. One is B dagger J A, and the other term plus is A dagger B. Yes. So three terms out of expanding these fellows, and twice as many because each of these guys is also a sum of two. A lot of these stupid terms. Now, my reduction finally comes. So I want to take on both sides trace of this guy over variables of the reservoir. On the left, well, it is more or less obvious. What I get is simply density matrix, derivative of the density matrix of the subsystem, of this A system. On the right, there is a lot of terms. Fortunately, half of them are zero. Why? Look, there are many terms in which we've got two annihilation operators sandwiched with the Bath operator, and and then traced. Exactly for the same reason as a single B was vanishing, also double B will vanish because it will destroy 2. Yes, it will destroy 2. So this is your note for our special reservoir. Often in literature you could find more extensive study in which this is not 0 and this is somehow elaborated because the state of the bath of the reservoir is different. Fortunately by us it is simpler. Now, for the same reason, this fellow has also trace which vanishes for exactly the same reason. Now, there are of course now also places where I need to evaluate trace of Bi dagger Bj with row B. Well, first of all, if I is different than j, it is again 0 because
This is different than this above, or
what?
how is it different?
I'm sorry. I'm sorry. I'm glad you're not asleep.
Yeah, and it wouldn't be true.
What? Yeah, it would be true, yeah. But what I want to say is that this is also practically always 0. In other words, this is proportional to ij delta function, yes? Because if this fellow will destroy 1 and this is different, then okay. However, when I is equal to j, this is very nice. This is just a mean value. It is I or j mode, yes? This is mean value of quantile. This is not enough. Encounter all this huge number of terms, we will be also getting traces where these guys are anti-normally ordered. Bi, Bj, dagger, row B. This is of course very easy, yes? Because as always when we see such a beast, then we add and subtract Bj, dagger Bj. I, of course, it's always again a delta function. And the value here is simply nj plus 1. So these are 4 conditions that allow us to perform explicitly the traces over the bath, over the reservoir, for this particular very simple reservoir. Huge thermal bath of temperature which does not care for what little comes out from our cavity. Okay? So now, as I say, half of the terms are 0. The other half, we know how to handle tracing over B. And what we are left with is still a lot of terms. And I will evaluate only one of them explicitly. All of them can be evaluated more or less exactly the same way. So the terms that we will get are ordered differently with respect to A operators. Since, as I mentioned before, we always need one B dagger, the other non-dagger, then because of interaction Hamiltonian mode, what will remain, will also have one A dagger and one A. Yes. No AA, no A dagger, because they are multiplied by similarly identical B's, and these are 0. So the only terms that we will get will have one A and one A dagger. However, both in terms of ordering, they can be either this way or that way, very much like with B's, and also with having one of this fellow on the left of row and the other on the right. In all possible ways they can be found, right? evaluate only one example. Done it rather carefully. So let us look at the typical example. Here is one of these typical examples. I had minus h bar 1 over h bar squared. I will put h bar here because you remember in the interaction Hamiltonian, I had always h bar in front times coupling G. Yes? Since I'm in the second order, there will be 2 h bars. Then there will be integral from 0 to t over v tau. And then I will have sum over all the J modes, squares of the couplings. In principle, there could be a double sum, but because of this property of a trace that was proportional to delta ij, I will always get only diagonal terms here. Now, I want, in this particular case, to evaluate the situation like so, with a rho of tau, tilde, and because this fellow is ordered normally, then what remained with the b's was anti-normally ordered. You remember, A dagger was always going with B, and A was always going with B dagger. So in other words, it used to be here B dagger. So upon tracing, I need here nj plus 1. That's the remnants of the B dependence. And finally, I need e to I omega j minus omega times t minus tau. Okay? And here the little hocus pocus will start. Our term, which is on the right hand side of a differential equation for the reduced density matrix, relates my density matrix of the cavity at time t to the density matrix at time tau, which is variable. The fact that there is this tau here and not some particular 0 of t is called a memory effect here. But memory effect because what the changes at present depend on the situation of the past. Yes, so it's a memory effect. There's a,
Is this the same as in the boundary of the...
yeah, sure. Sure. You remember in the second order, one Hamiltonian was evaluated at time t, this external one, yes. Only the other one was at tau, and then there was interrogation. So this sort of expression certainly will pop up. I come back to my cheating. Yeah? So what we don't like that the derivative at time t, there are many terms, but in all of them would have integral with rho evaluated at time t.
Why
tau.
we don't like it?
Why we don't like it?
This is
Because
the
the
solution of the same equation. So
well, because we don't like it because the resulting equation would be integral differential equation. We would prefer to have pure differential equation. In other words, we would prefer to have some operator acting on rho, but only on rho at time t. Yes. Of course, we are in the interaction picture, so our rho would not depend on time at all if no interactions. So the approximation, which is called Markov approximation, has a celebrated name. It's brutal. Okay. Let's take this as a rho of t and take it outside of the integral. Much better because the rest is just explicit function of tau and can be integrated over. Yeah? So, we already made this dramatic introduce t minus tau as the integration variable to make it nicer. If I change this variable, then integral runs from this new variable to 0. So it is like minus from 0 to this new variable. And that will cancel against this minus. H bar square also cancels. So this is, say, du from 0 to infinity. Sum over j squared times n plus 1 times e to I omega j minus omega times u. Well, if we have such integral, then what immediately comes to mind is that, oh, I already did, to go to infinity with the upper, I'm sorry?
Why do we keep this infinity here?
Yeah, because we are again cheating, yes. Instead of computing it for t, let's go to infinity. Well, then, easier said than done. Easier said than done because the shell oscillates like crazy and this integral does not exist. So, next, put epsilon u to make it convergent. And then, of course, go with epsilon to 0.
I really do not understand why this infinity should work.
Well, because, look, these are incredibly oscillating functions. So for very long times, then there will be so many oscillations that cancel each other that it does not really make much sense to remember about the finite value of this upper limit.
I agree that that does not really make sense.
Well, these are, you can find it in every textbook on this stuff. I don't like to talk to lecture about it, but sometimes I also sometimes have a perverse pleasure of telling about it, showing you how brutal tricks often lead to something which is of huge importance and I would say historical value. Yes? So, but look, once I made this sin, then I know what is this integral, and immediately you will see why I like it. Because upon integration I get 1 minus I omega j minus omega plus epsilon. Wow, we know it, yes? Again, it's this principal value integral times imaginary unit plus pi, yes? So it's, again, this p over 1 minus omega j I minus omega plus pi times delta omega j minus omega. Fantastic, yes? Now the last sin we are going to commit. This is somehow, this part somehow is again corresponding to some kind of the level shift or whatever, frequency shift, yes? It does not really deserve the name of a level shift, but it's a counterpart of that. Of course, in simple models, it pops up divergent, but it is so small that we will omit it. So, now, the other thing is nice, it's delta. And we can sum, or if you want, integrate over frequencies of these omegas. And then we get from this term a dagger a, rho of t, and you remember pi times modulus of j evaluated at the frequency of the oscillator. We were calling, last week we were calling kappa. And n plus 1 is retained. This time, here I should write nj, but this time without any subscript. This is the number of quanta at this frequency of the internal oscillator, yes? In the thermal state of on that oscillator. Very simple after 3 major courageous cheatings. As I say, there is a lot of these theorems. Each must be evaluated separately, but they are all of the same type. So these three tricks that I put out can be used. And then the resulting equation, which is this celebrated master equation, is d rho by dt is equal to kappa times n plus 1 times 2 times a rho a dagger minus a dagger a rho minus rho a dagger a
What is in this brackets?
where
Next to delta. Omega minus something. Oh, it's there on the upper. Yeah, on the upper, like on the very right. When you have this principal value expression.
I take delta and
What is the argument inside?
omega j minus omega, of course, in the denominator. And under delta, of course, also omega j minus omega. Omega j minus omega capital. Yeah? So this is one term, and the other term is plus kappa n. You understand that these fellows, all these three terms, come from everything that would have b dagger initially, yes? And these terms that are proportional to kappa times n, they come from the other normally ordered b's. And since all normally ordered b's go with anti-normally ordered a's, then these three terms have the form a dagger rho a minus a dagger rho minus rho a dagger. Oof. So this is our great achievement. It's not ours, of course. It is well known. You can find it in many textbooks. In some textbooks, the relation is even less comprehensible than what I was telling you. And there are many, I would say, generalizations. First of all, I already mentioned that of some interest in quantum optics is to consider reservoirs which are not in the thermal state, but in some other particular state. And then, of course, this is more complicated. Second of all, people studied memory effects. In other words, people looked at the correction which comes from not pulling this rho at times tau outside of the integral. And for some problems one can do it. And there are interesting little aspects of the open system dynamics which do depend on not making Markovian approximation. Then there is another direction of research, and actually very recent, over the last 2-3 years, in which people say, okay, this oscillator evolves according to this equation, for instance, to the vacuum. If I put n equal to 0, then it is dumping to the 0 temperature reservoir, or maybe some temperature state. And then one can take this evolving rho as a source in the equation for the density matrix for the bath. Something that very few people until very recently ever considered. And then you can see what sort of the havoc, so to say, this source makes to the bath. And there are some people, there is a whole group of people who are linking this with the observation, classical observation of quantum subsystems. They would say, aha, I have no idea how to observe directly single photons inside of the cavity. But if I would see what sort of minute as they are changes these 5 photons after leaving cavity would do to the reservoir, which is huge, which has a lot of degrees of freedom, then those maybe would already have a classical meaning, and then could be observed. So in other words, study of the open systems feedback on the reservoir became recently, over the last, I don't know, 5 or so years, the subject of I would say, fashionable research from the point of view what people call looking for the reality in quantum mechanics. Some people believe that in this environment there is this reality image, so to say, of the little system which radiates or interacts. So it's very hard to observe, if you want, directly. But of course, all these little directions, changing properties of the reservoir, forgetting about Markov approximation, maybe also not making rotating wave approximation, which is another direction. All this goes far beyond what I want to tell you, especially since we are coming near to the end of the semester. Also because this is really highly specialized subject. I would say that such a general purpose quantum mechanics course would really suffer if I would go deeply into.
The N is the Nj with J.
For J
equal to omega.
Energy, yes. For energy equal to omega capital. Yes. Just because of this delta, yes? Mm-hmm. Okay, so now let's use this equation for something. And I want to use it for 2 different things today. First, I want to think about the steady state to which this system should evolve for long times. We have our cavity. Who knows what the state initially is? But outside we know that there is a buffer temperature T. Well, the reservoir is for making this fellow go to some steady state, yes? So let's look for the steady state or stationary state which satisfies this equation. In other words, let's equate all this here to 0 and see what sort of solution do we get. I can look for the solution stationary in the form of pk, kk. Looking at the representation in the Fox space of this one single degree of freedom with operators A dagger, and frequency omega, which, by the way, fortunately we dropped out of the picture because we are in the interaction picture. That's why nothing oscillates anymore here. So what? I want to substitute this rho in all these terms and evaluate, yes? Easy is when I have A dagger A acting on this fellow, because whenever A dagger A acts on this, or A dagger A acts on this side, then I get simply K times the same fellow. Same operator. That is easy, yes? What happens if I have the first term, which is A, K, K, A dagger? What is it? Well, it is of course proportional to K minus 1, K minus 1. And what's the proportionality coefficient? You remember probably A acting on K gives this fellow times square root of K. So does this acting this way. So here I get simply K I need, of course, this. And that raises number of quanta. So I get k plus 1, k plus 1. And the coefficient, well, coefficient is k plus 1. Yes. What else do I need for the second part? For the second part, I need a, k. This I already have, sorry. I need a dagger, k, k. I think you already know what happens. A dagger pulls out square root of k plus 1, and this another square root, in other words, we get k plus 1 times again k, k. And the same if this is on the right. So knowing this, and then substituting this sum, and changing summation coefficient by 1 up and down when encountering this situation where either number of quanta is larger or smaller, and then equating to 0 all the terms multiplied kk, I get the following set of equations for these probabilities. If I equate it to 0, then it is immediately not, we can immediately notice that kappa I can drop, yes? Nothing depends on how quickly the system is talking to the reservoir. The final state will not depend on that. And so the equation that I will get is the following: n plus 1 times k plus 1 times p of k plus 1 minus k p k is equal to n times k plus 1 times p k minus k times p k minus 1. So this is set of equations for k equals 0, 1, 2 up to infinity. That is, probabilities pk must satisfy in order for this state to be a steady state of the cavity mode interacting with the reservoir at temperature T. And again, temperature T is hidden only in the mean value of quanta at this frequency. Yes. Okay. First very simple observation. Let's see what happens if I put k equals 0. Then what I get on this side is n plus 1 times p1. This is 0. Here I get n 1 times p0. And this fellow for k equals 0 is 0. So from here I get that p1 is equal to p0 times n divided by n plus 1. That's a good sign. You remember, in the thermal state, pk was n to the kth power divided by n plus 1 to k plus 1 power, yes? So, p1 to p0 is exactly n, should be exactly n to n plus 1. One can play this game for any k, and in particular one can substitute as pk and 2k divided by n plus 1. Well, 2k plus 1, but I will write k for simplicity. If I assume this and it is a solution, then this is not properly normalized. But then when I sum and divide by the sum, then there will be this additional 1 power here of n plus 1. So, I think it's boring, yes, to substitute this fellow here, 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 and checking that indeed this is the solution. So in other words, this little exercise that could be and should be completed tells us that, as expected, in spite of all the cheating we were doing, the stationary state of such an internal mode is, of course, a thermal state. What else could it be? Yes? If we would get it different, then I would say that this is not the equation that deserves a name, master equation or Lindblad equation or something like this. Or maybe even Kosakowski-Lindblad.
It should be k plus 1, right?
Not necessarily, yes. If I do not put it k plus 1, then these are not normalized properly. Some of p's is not equal to 1. There only this, yes.
So we can multiply it by p0.
What?
So we can multiply it by p0.
Sure, yes. I agree, yes. Okay, so this is my first exercise, and I have one more for you. And it is the following. Now, let me specify, so to say, my situation for the bath which is at 0 temperature. In other words, let's assume that what is outside is a vacuum. Well, if so, then the second part is missing, yes? Because I have n here. And what I'm left with is this part. I have in the notes that you've got already a week ago, I have it not in the interacting picture, but I even went back to the Schrödinger picture, and that is not very different. It only means that there are these I omega terms. By the way, in the notes they are little omega, but sorry. And it looks like this, minus I omega, A dagger A with rho. So this was missing here, but it's not very important, not very relevant part, times kappa. So it is this kappa, and all what you have here can be combined into A rho. Yes, A rho, comma, A dagger, plus A rho, A dagger. It is nothing else but this fellow, but these guys just written down in the form which you can find in many papers or in some textbooks.
Where is this omega from?
I'm sorry? Well, I wrote the same equation, but in the Schrödinger picture, not in the interaction picture. So I worked back my commutator with the free Hamiltonian. Yes, that's the only thing. I just wanted to be more or less in agreement with the notes that I handed out. I'm still not in complete agreement because in my lectures I'm always calling frequency of this oscillator capital omega, and there it is little omega, but probably you can forgive me. So now, observation that I want to make, use of actually next week, is the following. If I look at all these terms, or if you want, all these terms, then what these two terms do is something very similar to the standard free Hamiltonian. These are A dagger A rho minus rho A dagger A, yes? Well, there are two minus signs, that's true. But other than that, it's very similar. In other words, as we were doing this exercise before for the thermal state, if I take some Fock state, rho for some Fock state, these fellows do not at all change the number of quanta in the state. What this fellow does, well, this fellow destroys one quantum here, because it both destroys one guy on the left and one guy on the right. There is a jargon which is now very common. This term, people call it a jump term. And these two terms people call, I don't know, Prague indicators. I want to tell you more about this use of making this distinction, keeping these guys separately and then discussing what they do to the state next week. But what I want to do this week, I want to indicate, without doing copy calculation on the blackboard, because they are simple and straightforward, that if we have our cavity initially in some Fock state, then we can solve exactly for the time-dependent Rayleigh equation. To this end, we will do something analogous to the exercise before. Namely, we will assume first that our initial distribution is just delta of Kn, yes, so that we start with n photons inside, and then we want to look at P K of T. Full operator would be again like this, summed over K from 0 to infinity, and this will be our answers for the time-dependent solution. So, what we do? Well, we substitute this now to our equation. Again, we know very well how to evaluate all these terms, a dagger and a dagger and so on, shift everything, and then one immediately, very quickly finds that dpk by dt is equal to minus 2 kappa k times pk plus 2 kappa k plus 1 times pk plus 1. So this is a set of infinitely differential equations. And out of this set of equations, we can very quickly compute the moments. Compute first something trivial, namely equation for the sum of pk, total sum, total probability. I have to sum over all k's. Okay, I sum here and I sum here, and since summation is over everything, then this sum and this sum are identical, signs are different, and in fact, for the sum of pk, I immediately get something very simple, which is kind of nice, because it means that our evolution is not producing or destroying any probability. Then, if I take and multiply everything by k and sum over k, then I will get equation d by dt for the mean value of quanta. I will change this in time, and I'm sure that you can do it yourself. this would be 2 kappa times mean value of n. Very nice. You remember that exactly the same equation was true in our Heisenberg picture treatment last week. From this, of course, we see that mean value is mean value at 0 times e to minus 2 kappa t. Again, just like a week ago, this goes nicely to 0. And then I can also multiply this fellow by k squared to see what is the equation which is satisfied by the mean value of n squared. A little bit of fiddling with these equations, and what you should get is minus 4 kappa times mean value of n squared plus 2 kappa times mean value of n. So how do we solve it? It's very easy. We plug in this here and then treat this as inhomogeneous equation for mean value of n squared and then integrate, and that's easy. Then we can take this n squared, subtract square of the mean value to see how the variance behaves, how does it evolve, and to surprise, surprise, it evolves exactly the same way as last week. Better do it like this, because otherwise one of these things would be wrong. Yes. So I remember the formula last week. So the variance of n squared of t was, what was it? Was e to minus 2 kappa t, 1 minus e to minus 2 kappa t times variance at the beginning. No. Times mean value of quanta at the beginning, squared probably, I don't remember. But, no, not squared, like this. And the same discussion applies, yes? It starts from 0 and ends up at 0, and there is some maximal variance somewhere in the middle. And just as last week it has the same interpretation, there are many different trajectories of decay from n photons to 0 photons. And all these paths are taken, and for this reason, even if we know that the variance at the beginning and at the end is 0, it must be non-zero somewhere. So, that's all I wanted to tell you today. You've got a rather powerful tool now for many different studies. Maybe I finish with one remark. Something which is in many books is, of course, very similar application to the spontaneous emission problem. This is well known in the books, as I say. But the same techniques of master equation were developed and applied by several groups, including us, means mostly Pawłowski and myself, in his PhD, and then he's still continuing doing this for the losses of the condensate. Some of you, most of you, attended his talk yesterday, yes? As almost always, at some point he says, okay, there are 1 particle, 2 particle, and 3 particle losses for the condensate. And then let's write the general master equation of this Lindblad form, except that, of course, this destroying and constructing operators are much more complicated if you really want 2 and 3 particle losses. He's also telling correctly that when we first wrote it, we were trying also to derive somehow rigorously these things for 2 and 3 particle losses, and we did not succeed, so we had to cheat even more to get these equations. But they are widely used, everyone is using them now. So until someone finds that they are completely wrong, they are believed. Yes. Single particle losses go the same way, yes, all the calculation is the same. So I don't know when Pawłowski was doing his PhD maybe 5 years ago. So at that time we were introducing same methods to this new problem. And that is indication that there are many other problems, certainly in solid state physics and in many other areas of physics, where these techniques are applicable and one can derive proper master equations and use them for various decaying, for various open quantum systems. Okay, thank you. We stop recording, otherwise some jokes would be... Oh, let me tell you a joke.